So now let's look at section 3.8, where we learn about solving equations using inverse matrices. So we've already learned several ways. When you set up a matrix, you can, of course, go to the calculator, or you can use the Cramer's rule, use a determinant, and now let's look at using the identity matrix. So what is the identity matrix? Well, it's a square matrix when multiplied by another matrix, it equals to the same matrix. So identity, remember we had seen that. So like when we have like addition, if you add 0, you get the same thing back, right? And so the same thing kind of happens here with the identity matrix. If you can find a matrix that you multiply by another matrix and you get itself, then that's your identity matrix. So a square matrix, of course, we had discussed this, is a 2 by 2. So it forms a square, right? So it's something like this. And a 3 by 3, of course, is, 3 rows, 3 columns. And so what you have, though, is the identity matrix. If you notice, ones run across a diagonal this way. So it's 1, 0, 0, 1, 1, 0, 0, 0, 1, 0, and 0, 0, 1. So you have your ones coming that way. Now, the identity matrix for multiplication is this right here, right? So if we take any matrix, let's say matrix A, which has these elements, and you take the identity matrix and you multiply them together. So remember the rules of multiplication. When you're multiplying matrices, you're taking this first term times this one, and then this term times that. But what actually is going to happen? If you notice, A times 1, which will give you the A, but then you don't have to add anything else because B times 0 gives you 0. So if you notice, that's kind of going to be the case when you do this. So you actually, when you multiply these two together, you actually get the original matrix back. So therefore, this is the identity matrix for a 2 by 2. Of course, then this would be the one for a 3 by 3. Now, what is an inverse? An inverse matrix. So an inverse is two n by n matrices that are inverses, like kind of opposites of each other, if their product is the identity matrix. So if you take any matrix A and you multiply it by its inverse, or take the inverse and multiply it by the original matrix, then you should get the identity matrix back. Okay, so we're going to look some examples and you'll see some more notes in just a bit in your packet. So the inverse of a 2 by 2 matrix, let's say you have a B, C, D, right? This is your matrix. And you find, how do you find the inverse of that matrix? Well, this is what you do. You put 1 over, and if you kind of notice this is a determinant kind of thing, right? Because you did A times D minus B times C. So to find the inverse of a matrix that's 2 by 2, all you do is take the elements, take the determinant AD minus BC, put it underneath a 1. So that is a number that you're going to get here in the front. And then look what you do. You put the matrix, look at the order. So instead of whatever number you had up here for A, you switch it with the D. So see right here, you took the A and you switched it with the position of D. So you flip these, and what do you do with these? Look at that. You keep them in the same spot. However, you make them the opposite of what they used to be over here. So now instead of having C, you're going to have negative C. Instead of having B, you're going to have negative B. Whoa, so that may seem a little, like you're trying to figure it out. That's okay. We'll do some examples to see how that is done. So if your determinant of a matrix is 0, then it doesn't have an inverse, right? So see, can you see why? Because if there's a 0 right here, 1 divided by 0, we don't have the means of calculating that. And so therefore you couldn't be able to get the inverse matrix, okay? So let's go ahead and look at some matrix equations which can be used to solve a system of equations. So a matrix equation is pretty much, we've seen the way we set it up. However, since it is a matrix equation, you actually keep the variables, the x and the y. Remember the others, you take those out, you just kind of keep the coefficients like the 1, the 2, the 3, the -6. But to make a matrix equation, what you do is you actually take the term, so like 1x plus 2y, and then 3x minus 6y is equal to, you create another matrix where these are your constant, like the answers over here, right? So the equal to part, so you place them here. So if you look at the parts that you create, now you kind of, the coefficient matrix would be all the numbers. So 1, 2, 3, -6, 1, 2, 3, -6. So then you break it up. This is your coefficient matrix times, take the variables that you're using, the x and y. This is called the variable matrix. And all of that would equal to your constant, which the constant matrix, which is kind of the answers. So notice how you could break this up in the pieces too. So that would be called a matrix equation. Now, what about an augmented matrix? This is the most common. This is the one I showed you that I entered into the calculator several sections ago. So an augmented matrix has the coefficient matrix, so all your numbers, and the constant term. So pretty much this A part and this B part right here. So notice how you create an augmented matrix. So you say matrix A is, and then you place those bars, and then here we go. We start. So 2, 3, 4, 2, 3, 4, 1, 2, 1, 1, 2, 1, 1, 3, 2, 1, 3, 2, and the answers are 1, 12, -1, 1, 12, -1. So pretty much you just take the coefficients, which are the numbers in front of the letters, and place them in A, and then you place like a little bar, and then the answers also as well. So it's just really the 2, 1, 1, 1, 2, 1, 1, 1, and so on. The augmented matrix is the one that can be placed in the calculator to solve when you do the row reduced echelon form. So now we can look at your packet, and in your packet you've got, again, the vocabulary that is going to be necessary for this section, and it's in your notes, so you can look at that as well for additional resources. You also have the idea of what is the identity matrix, and we discussed that with the diagonal having the ones there. And so how can you find if these two are inverses of each other? Well, remember, if we multiply them together, x times y and y times x, and they give you back the identity matrix, then you're good to go. Then they are inverses of each other. So here they show you the steps in solving that. So you could just practice multiplying these out to see if you do end up getting the identity matrix. So for example, in this case, when they multiplied A times B, then B times A, they are not inverses because you don't get that identity matrix, the 1, 0, 0, 1. So just a matter of practicing these to check. So again, checking if they're inverses, you multiply them C times D, and then D times C. If you get the identity matrix, they are inverses. Now, how do you find the inverse of a matrix? Well, let's go ahead and go through those steps. So if you notice, the first thing you do is you find the determinant, right? So the determinant of this particular matrix is, remember, you take -1 times a -2, and then you subtract the 0 times 8, which in this case is 0. So that's what they did. -1 times -2 gives you a 2, and then 8 times 0, of course, gives you 0. So 2 minus 0, you get a determinant of 2. So the determinant is not 0, so then we can proceed. So now let's look at the next slide, which kind of gives us the how to set up the inverse. So we found the determinant. Remember a little while ago we found that AD minus BC was equal to 2, which is what is here. And so they already wrote it right there. There's a 2. So it's 1 divided by that 2 that we found. And then remember what I said to do to these numbers, a D, A, C, and the -B. So let's go back to the original matrix and see what you're going to do. So remember how you had to, it's no longer A, B, C, D. You flip these two. So notice how if you come back over here, -1, -2, you're going to flip them. So they're going to come -2, -1. And then what do you do with the C and the B? Well, you make them negative or opposite of what they used to be. Right here, it's an 8 and a 0. So you make a -8, and then 0 has no sign, right? So you just keep the 0. So now you take that number, the 1 over the determinant, 1 over 2, and it's a scalar. So now you're going to multiply that with everything inside. So remember, it's kind of like distribution. You're going to multiply that 1/2 times everything inside. So if we do that, half of 2, I end up with, it's a -2, right? So I end up with a -1. Half of 8 is -4. The half of a -1 is a -half, and of course half of 0, well, is still 0. So that's how you find an inverse of a matrix. So then what you're going to be doing is working on some of the problems to do just that. So remember, to find if you have an inverse, multiply them, x times y, then the opposite, y times x. And when you do that, you should be getting the identity matrices back. If you do, then you do have an inverse, right? Those are inverses of each other. And so basically, you're going to be doing that with these questions here. Then they're going to ask you to solve the system of equation and using that, setting it up like a matrix. And so basically, the example is right here. So you just need to go through this example. They show you the steps, and you saw it. You saw me demonstrate it also in the notes, and so that's how you can find the different parts of a matrix, a variable matrix, coefficient matrix, of course, and so on. So then you have some matrices here. So they ask you to solve the system of equations. At this point, you have a lot of different methods. So practice on the different methods to check your work to see if you're doing the right steps. And then the same thing in the practice, just additional practice of the same, trying to find the inverse of the matrices. Of course, you have a little bit of word problems, little coding for the computer use as well.